Welcome to Posthammer pervasive browser-based Rowhammer attacks with postponed refresh commands. My name is Finn and this is work done together with Patrick and Kaveh from the computer security group at ETH Zurich. With Posthammer, we show that the majority of DDR4 chips is vulnerable to browser-based Rowhammer. What does this mean? This means that you, as a victim, visits a web page while in the background, the attacker hammers on your machine to then obtain a read-write primitive in the JavaScript process. We found that the majority of DIMMs is vulnerable, so 17 out of the 28 DIMMs in our testbed was vulnerable to this attack. The attack takes about 15 minutes on average and has a success rate of about 40%. So what did we learn? I will now share 3 insights with you and then say something about the exploit. The first insight is related to refresh commands. Refresh commands are sent to DRAM by the memory controller periodically. And it's this periodicity that the mitigations rely on. So here, whenever the attacker comes to hammer, there's always a mitigation to stop the attacker. However, the standard also allows refresh commands to be postponed. And this is something that the attacker can induce. So we measured the attacker's ability to postpone refresh commands. And then what happens is something like this. So the attacker can create a period of, let's say, mitigation inactivity during which the attacker can hammer freely, boosting the the effectiveness of the attack. The second insight is related to the difference between uniform Rowhammer patterns and non-uniform Rowhammer patterns. In a uniform Rowhammer pattern, there's either one aggressor or several aggressors, but they're all hammered equally, and this does not make them that effective. In a non-uniform pattern, however, there's always several aggressors or different aggressors that target different rows, and they're not hammered equally. So in this example, the green aggressor will be hammered more often than the other two, and this means these patterns are generally more effective because the mitigation needs to choose certain aggressors to mitigate and generally cannot stop all of them. The challenge lies in the combination of this non-uniformity combined with the browser context. So launching a non-uniform pattern from the browser is challenging. And this has to do with the fact that to hammer, you need to reach DRAM, right? You need to bypass the caches, reach DRAM to activate the rows, and therefore hammer. And natively, this is relatively easy because there's this cache line flush instruction that you can use to send any aggressor you like to DRAM. And this allows you to create arbitrary patterns, very complex patterns that also have a lot of non-uniformity. However, in the browser, there's no such instruction and you need to use eviction sets. I will say more about eviction sets in a moment, but they generally make it much harder to send an aggressor to DRAM. So what do these eviction sets look like? Here I've illustrated a cache set, which is a set that contains a bunch of addresses. And in order to, so whenever you access an address, it moves into this cache set. And in order to have an access go to DRAM, we need to get the address out of the set. So we need to evict the address from the set. So let's say that our aggressor is an address that is in this set. Then what you would traditionally do is you would find other addresses. So each of these boxes here represents another address, other addresses that map to the same set. And by accessing all of them, they are continuously replacing the contents of the cache set. And this means that the addresses are evicted from the set, and therefore when you access them, the access goes to DRAM. This, however, creates a very slow pattern. If you would hammer like this, it's very slow because all accesses go to DRAM, and it's also still a uniform pattern, right? Because we just have one aggressor, and it's just this aggressor going to DRAM. Now, to improve the situation, what you could do is use minimal eviction sets. So when I use a minimal eviction set, I'm not using this these two sets of addresses, but instead just one, and then I make the observation that actually I just need one more address so that the addresses together do not fit into this set to create eviction. So now I need to be a little bit more careful with the way I access the addresses. So I need to be careful about the order in which I access them. But this is possible and makes the pattern a lot faster. It's still slow, however, because all the accesses do go to DRAM. So not just my aggressor, but all the others also go to DRAM. And it's still a uniform pattern. To improve the situation even further, what you can do is use cache hits. So instead of having all addresses go to DRAM, I can try to pin certain addresses to the cache set. So by accessing them more often, I can make the cache replacement policy keep them in the caches. So now these smaller boxes represent addresses that I access more often than my aggressor and this other larger box, this one other address that will also go to DRAM. And the result is that I have more accesses in total, but I have more cache hits, which are much faster than the cache misses. And now I have just two cache misses, namely my aggressor and then this other box. So this is pretty fast, but still a uniform pattern. Now, to not waste this extra address here, to not have it just for eviction, what I can do is I can try to make this an aggressor as well. So now I get two aggressors. This is better, right? Because now I'm hammering very efficiently, but the pattern is still uniform. So to improve the situation, what we've done is introduce the notion of lanes. So with lanes, you can create patterns that look like this. And now we can create a non-uniform pattern. So by combining these minimal eviction sets that we now call lanes, you can create a pattern that looks like this. And the very important thing here is to note that I cannot repeat the same lane twice. So I cannot have the first lane with the black aggressor and then repeat it. So I cannot create arbitrary combinations, but as long as I alternate the aggressor in my lane, the eviction will work. And therefore, if I create a chain that looks like this, I can get some non-uniformity because now the black aggressor is accessed twice, while the others are accessed only once. So I can get some kind of non-uniformity. So this is what we mean by a lane. And this creates fast patterns that are also non-uniform. Some examples will be the following. So this will be the one that I've shown on the previous slide where we have 50% for the black aggressor and 25% for the other two. You can also make it longer to get different ratios. And there are many more combinations possible. Finally, the third insight that I would like to share with you has to do with the fact that with just very few patterns, the attacker can have a big impact, which means that with just two types of patterns, the attacker can bypass all mitigations. So this means you don't need to target, as an attacker, you do not need to target a specific dim. You can create a kind of template pattern and then make only minor adjustments and you'll be able to trigger bit flips on most dims. So what does this template, or let's say this generic and very strong pattern, what does it look like? So recall that a pattern could look as follows, right? The chain of lanes that I've shown before. So now just to give you some idea of what this effective pattern looks like is this. So I start with, again, two lanes that contain two aggressors, and this is the uniform part of the pattern. So now I have a very simple uniform pattern that I'm repeating two lanes, that I'm repeating many times. So these two aggressors are hammering hard, but it's uniform. And just this on its own would not be enough to trigger bit flips because the mitigation would detect it. But now what I add to this is these extra lanes, B1, 2, and 3. And as you can see here, there is non-uniformity that contain a lot of aggressors, but they're not really hammering. They're rather to distract the mitigation. So now I have 5 lanes in total that I connect into a single pointer chase. And then if I take this pattern It requires a lot of eviction sets. And I combine it with refresh postponing, I have a very strong pattern that will work on most things. Now something about the exploit. So the exploit is very complex, and I would really encourage you to look at the source code because it's all available. But I will just go over the exploit in 10 steps to give you some idea. So at the core of the exploit is the idea of type flipping. So what we do is we use the bit flip to change the type tag of JavaScript objects. In particular, we use the bit flips to turn array references. We turn array references into floating point numbers and the other way around. So a floating point number becomes a reference and a reference becomes a floating point number. We start the attack with allocator exhaustion. So we allocate a lot of memory, and this forces the allocator to allocate larger blocks, to split up larger blocks. And this means we are able to get contiguous memory. And contiguous memory allows us to build an eviction set relatively easily, because remember, all these patterns consist of eviction sets. So we use this memory to build just one eviction set, but once we have one, we can use it to build many more, for which we do not require contiguous memory. So now we have a lot of eviction sets, and we can use it to build patterns. So now we can already start hammering, and we hammer using the patterns that I've shown you before, and we use slight variations, and we constantly swap the eviction sets to search for exploitable bit flips. Now we found the exploitable bit flips, and because these exploitable bit flips, we need two bit flips, one 0 to 1 bit flip and one 1 to 0 bit flip at the right location. So they are very particular bit flips. And this means that once we found them, we generally find more bit flips. So we find other bit flips. And so the problem is that we need to just trigger the bit flips that we are interested in and not these other bit flips. Now, to do that, there are several techniques, and we also wrote a paper about this. It's called soft hammer, and the idea is to hammer softly on the bit flips that you don't want. So we hammer softly to prevent undesired bit flips and just trigger the bit flips that we are interested in, namely the exploitable bit flips. Now it's time to launch the exploit, which means that we release the arrays that we have been hammering on, right? Because this is attacker-owned memory. It's not so interesting to trigger a bit flip in your own memory. So we free these arrays, and then we immediately allocate so-called target arrays. So these are the arrays that we want to land our bit flip in. So now the bit flip ideally moves from our array to the target array. And we found that this step has a success rate of about 80%. So this usually works, but it does not always work. And then we hammer again to find out where in the target arrays the exploitable bit flips are. Now it's actually time to use them. So now we re-trigger the first bit flip, which is the 0 to 1 bit flip, and it turns an array into a floating point. Then we use the second bit flip, 1 to 0, that turns a floating point into a string reference. Again, the first bit flip, the 0 to 1 bit flip, so it's the same bit flip that we used the first time. And now there's of course some work that we need to do in between. But now we are able to create a valid but a fake JavaScript array. So we have created an array of which we control the data pointer. So we can read and write from this array, but at the same time we can decide what the array is reading from. And this is effectively a read-write primitive. So we control the array's data pointer, which normally is not possible, of course, and this allows us to read-write anywhere in the address space of the JavaScript process. And this attack is free of huge pages. Remember, in the first few steps, we're doing this allocator exhaustion, and it's pretty reliable. So the success rate is 40%. And when it does not work, it's usually because we have too many bit flips and we corrupt something that we should not corrupt, and then we segfault. The artifact, again, is available, and I highly encourage you to have a look, and it should also work, so you can run the attack yourself. So to conclude, we've shown that with refresh postponement, the attacker can create stronger patterns. The attacker can use lanes for non-uniformity. And finally, with just very few patterns, the attacker can have a big impact. Thank you for your attention.